Hey guys, welcome back. And I wanted to take you through an example of the problem that was shown to you in the CK12 reading, where we're combining specific heat calculation with heat of fusion, heat of vaporization. Okay, so here's an example of a heating curve problem. The heating curve, as you'll see in just a minute, is actually just the graph that we draw to help solve the problem. So it says how much heat in joules is needed to bring 25-gram sample of water from minus 45 degrees Celsius to 250 degrees Celsius. So the first thing I want to do is establish what I know about water. That's going to be helpful in order to draw our heating curve. So a couple things I know about water is I know where it freezes and I know where it boils. And so water has a freezing point that is, I'm just going to draw it on the graph. Um, Water freezes at 0, and this is going to be temperature on the y-axis in degrees Celsius. So water freezes at 0, water boils at 100. Okay, so I'm just going to mark those two temperatures on my graph. Notice I didn't put 0 down here at the origin because this problem actually starts at minus 45 degrees Celsius. So we're actually going below 0 for this problem. So those are the other two temperatures that I want to plug into my y-axis here. Um, my starting temperature, which is minus 45, and I'm just going to put that, we'll just put it at the very bottom there. And then the very, or near the top at least, and this doesn't have to be to scale, this is just a visual. Notice I'm not counting out, the grid marks and saying, okay, uh, you know, not making the 250 quite as high up as I should, not making everything to scale. It's just a visual, all right? And you'll see in just a minute why it's so helpful, so important for solving this problem. So what we're really graphing here is the temperature change as a function of heat added. Or you could think of it as we're putting this sample of ice on a hot plate and we're just cranking up the hot plate and waiting. So over time, more and more heat is added. So maybe a big block of ice, put it in a beaker, um, drop that beaker on the hot plate, crank it up, and just kind of leave it going for I don't know, 30, 40 minutes. And what happens to the temperature and how much heat is required there. Okay, so the first thing we have to understand is that it's physical. Like what physical state is it in at minus 45 degrees Celsius? Well, if its freezing point is 0, and again, you don't have to memorize that, but that's a pretty uh, most people probably know that for water. 0 degrees Celsius is where it melts, where it freezes. It's what the Celsius scale is based on. So anyway, it freezes at 0 or it melts at 0 depending on how it's starting. In this case, it's starting as a solid because it's below the freezing point, and it's going up to 0. Okay, so what's happening here is from minus 45 up to 0, the temperature is going to be rising as we heat that block of ice on that hot plate. Now, as we learned last time, the next thing that's going to happen is melting, and melting does not involve a change in temperature. That ice and water combination is going to stay right at the melting point until all of it is melted. Okay, so if you can imagine a glass of ice water, if that glass of ice water is well mixed, it's going to be the whole sample is going to be pretty much 0 degrees Celsius. Um, and and pretty much every glass of ice water you've ever drank uh, is going to be right around 0 degrees Celsius, depending on how well it's mixed. And that's because what's happening inside of that glass of ice water is you have melting happening. And as long as melting is happening, the temperature of our sample doesn't change. It stays constant because melting is absorbing the heat that we're adding. The melting process is absorbing the heat that we're adding. So what we see is a plateau on our graph. So that right here represents melting of the ice, our 25-gram sample. Okay, then once it's all melted, so once we're to this point, then the temperature can start to rise again. And it's going to do that all the way up to 100 degrees, which for water happens to be the boiling point. Okay, so once we get to the boiling point, so now we've got the beaker, it's all liquid, it's going up and up and up and up, 80, 90, 100 degrees, and then it starts to bubble and boil. At that point, the temperature, if you had a thermometer in there, would stop rising again, because what's happening there is boiling or separating of the molecules, the water molecules. That process is absorbing all the heat that we're adding. So the temperature plateaus again, right? Then once all of that sample has turned to gas and there's no liquid left, nothing left to boil, if we continue to add heat to our sample, the temperature of that steam, that gas, would in fact continue to, or would start to rise again, okay, from 100 up to, in this case, 250 degrees Celsius. So I'm going to draw my line going up again. Okay, so we've got 5 separate things happening here. So first we have the 25-gram sample going from minus 45 degrees Celsius up to 0. Then the second thing we have happening is it's melting. Then that melted ice that's now liquid is going up to 100. Then it's boiling. And then that gas is going up to 250. So that's a lot happening, but it actually breaks down into very simple steps. And so what we're going to do here is we're going to be given a bunch of help on this. We have 3 equations that we're going to be using. Anytime the temperature is changing, so I'm going to highlight that in green. Anytime we have a temperature change, we're going to use this equation. Q equals C times M times delta T. Okay? Because we have a temperature change. We're going from, for example, minus 45 up to 0. So temperature change is delta T. So that equation makes sense to use for those 3 steps. Okay? Then, anytime we have a phase change, we're going to be using one of the following equations. We got, so when we have a phase change, like, for example, down here, when we're melting, highlight that in purple, we're going to use our heat of fusion equation, which if you remember from last time is simply mass times H fusion, okay? And then we have one more process, one more step, and that is boiling. So let's go with blue for that one. So boiling is up there, and the equation that we're going to be using for that one is going to be very similar to the heat of fusion, but it's going to be heat of vaporization. Okay, so this is a 5-step problem, and it really seems daunting. Like, it seems like, man, this is too much, can't do all this. But you're going to see that it's actually just a bunch of multiplication and addition. It's really, really simple. Okay, so we're just going to do this one step at a time. To keep things clear, we're going to label very clearly what each step is. I'm going to call, excuse me, this first one is going to be 1. Our first plateau is going to be step 2. Our next little incline there, where it's liquid being heated up, we're going to call step 3. The second plateau is step 4, and the last incline is step 5. So we have 5 separate calculations, and then we're just going to add up the answers. And the calculations are simple because they're just multiplication. Okay? So let's look at step 1. So step 1, we have a change in temperature, right? It's going from negative 45 up to 0. So which equation are we going to use for step 1? Okay, so you should have said this one, right? Because it's got the delta T, it's got the temperature change in it, so therefore it makes sense that when the temperature is changing, we're going to use that top equation. Okay, so let's go ahead and do that. So step 1, so I'm going to find the heat for step 1, the Q, by using this equation. And here's where we got to be careful. Specific heat, C, remember if you remember from last week, that's what that stands for. The resistance to temperature change is different for a substance depending on what physical state it's in. In this case, it's a solid. I'm sorry, yeah, in this case it's solid ice. So what I'm going to do, I'm going to grab a table here that gives me all the different specific heats of my substances in my different states. And you can see here, and you never have to memorize any of this stuff. This is provided for you. You know, it's a constant. So water as a solid, this bottom line here that I've got highlighted, has a specific heat of 2.06 joules over grams times degrees Celsius. So for C, this guy right here, that's the number I'm plugging in. I'm going to say 2.06 joules over grams times degrees Celsius. Now what's up next? We have mass, right? Well, for this problem, the mass was given to us as 25 grams, right? So that's going to be the mass every time. Anytime I see M, 25 grams. Now, what up next we would have delta T, right? Well, what's the change in temperature here? It's going from negative 45 up to 0. That would be a 45 degree Celsius temperature change. And if I just simply multiply 2.06 times 25 times 45, I'm going to get my answer. And I'll go ahead and do that for you. Okay, so that gave me 2,300, and I'm just going to round it to 18, and that would be joules. All right, so we just took care of step one. Okay, step one took us from minus 45 up to the melting point, and then step two, we have this plateau, right? And it's melting. So which equation are we going to use this time? Remember, the temperature is not changing. Okay, so you should have said, since we're melting, if you remember from Monday, from last time, that when something is melting, we use heat of fusion. So we're going to use that little purple equation up there for step two. So Q is going to be mass, which again is not changing through this entire process. It's 25 grams the whole time. Okay, and then we're going to multiply that by the heat of fusion for water. And again, you don't have to memorize this. I'm going to provide this for you, and let's go back to our handy table here. The heat of fusion for water is 334 joules per gram. All right, so that is a constant. Okay, so 334 joules over grams. And I'll go ahead and do that multiplication too. Okay, so that's going to be 8,350 joules. All right, and then the next step. So now we're on to step three. Step three, we're increasing the temperature once again from 0 up to the boiling point, from melting point to the boiling point, from 0 to 100. So if we're increasing the temperature or changing the temperature at all, which of these three equations are we going to use? Okay, so hopefully you said our green equation on top here with this specific heat in it because it has change in temperature, right? And that's what we are in fact doing. We're changing the temperature. Okay, so let's see, that's going to be step three. So Q equals, now again, remember we're not going to use the same specific heat that we used the first time when water was solid because now it's a liquid. So let's go ahead and go back to our handy little chart here. Oops, not changing that. Okay. So the specific heat of water as a liquid now, because we're between the melting point and the boiling point, so it's a liquid, and that's 4.18. Okay, so let's go ahead and use that as our specific heat, and that is joules over grams times degrees Celsius. Our mass is still 25 grams, and our change in temperature this time is going to be from 0 to 100. Remember, we're just doing it for this step only. So we don't want to look at the total temperature change. We're going to look at this temperature change for each individual step, and for this step, it's going from 0 to 100. So that, of course, is a change of 100 degrees, right? And then we just multiply. Okay, and I got 10,450 joules. All right, and then the next step, step four, it looks like we have another plateau. We're boiling the water. So which equation are we going to use up here? Okay, So we are going to use our heat of vaporization, right? So anytime we're boiling or condensing, that's what we're going to use. Our mass is still 25 degrees, or sorry, 25 grams. The heat of vaporization for water is a constant, so it has to be looked up. And here it is right here, 2260, 2260. So there we go. And that is joules over grams. Go ahead and do that math real quick. All right, and this time I get a whopping 56,500 joules. Okay, takes a lot more energy to boil water than it does to melt it. So that's why that number is so large. And then the last step, what do you think here? Step 5. Temperature is changing, so which equation am I going to use? All right, so you should have said the specific heat equation, the top one, because we have a delta T, we have a change in temperature. It's going from 100 all the way up to 250. All right, so that is going to be my step 5. And let's see, it looks like yeah, I'm going to do that in green. Trying to keep my colors coordinated here. So Q equals, now again, the specific heat of water as a gas is going to be different than it was as a solid, which was 2.06, or as a liquid, which is 4.18. Let's go ahead and bring that table back in here. As a gas, it looks like it is 1.87, right? So 1.87, our mass is the same. It's still 25 grams. And our change in temperature this time is from 100 up to 250. So that's a 150 degree temperature change. So I'm going to do this multiplication real quick. And so I get 7,000, and I'm just going to call it 7,013 rounded. All right, and then my last question for you is, according to the reading that you did, what am I going to do with these 5 numbers, my 5 answers, to answer the question? What kind of math am I going to do to get my final answer? All right, so you should have said we are going to add them up, right? So let's go ahead and do that. Okay, so I got an answer of 84,631 joules. And again, the question we were answering was, we go back, and I know it's been a long process, but how much heat was required to take this 25 gram sample from minus 45 all the way up to positive 250? I know that's a really long problem, but hopefully you didn't find any specific step too difficult. If you did, please email me questions or stop by our Zoom sessions. I'll see you guys next time.